Hello everyone. So this is Zubair Akhtar, and this is a course on filters, microwave filters for RF and microwave frequencies. So before beginning with that, so let me explain why we are needing filters for microwave circuits. So let's come up with the kind of applications that we are seeing in real practical applications. So suppose there is one TV transmitter. It is sending a signal to a satellite, say microwave signal, and then we are receiving these signals at our homes to run our, say, TV. So what's going on? Say suppose this is sending some signal in frequencies and it is also receiving with the satellite. So this is our antenna, and here antenna receives the signal and we need some sort of filtering because this antenna can receive any signal. Say suppose if you have, this is FR, so this is frequency scale, so there might be other frequencies as well, so this antenna cannot receive, but we want to receive a fixed signal that we intended to use, so that's how we need a device which is called filter for such purposes. So filter is used for many of the communication circuits. This is like one of the example of satellite communication, so video signal transmission through satellites. Maybe you can consider as an example of mobile phone. So you have mobile phone, GSM, CDMA. So all like other interfering signals, frequency you want to avoid. So you need to have a device which is called filter that can suppress the out of band signals. So let's discuss more about this. So we have seen the position of the filter. It's just after our antenna, and it is sending the filtered signal to another device. Usually we have LNA. So this is low noise amplifier. So here is the filter. So by seeing this block diagram, we can say something about the filter. Number one, it is a two-port network because it is taking signal from first, this is like input port, and it is giving output at this point. So there are two ports, one is input port, second is output port. The second thing that we have recently discussed, the job of the filter is to pass the signal in desired frequency range. Say it is from one frequency F1 to F2, and the other third characteristic of this is to reject other frequencies signals. So we want something to pass, we want something to reject with this type of device in electrical network. So in overall, if we want to define the filter, so filter is a two-port electrical network that passes the signal of required frequency range, sometimes this also known as pass band, and reject all other frequency band. This is sometimes also called as stop band. So now we have seen the job of the filter, then we have seen the position of the filter in a communication network, then we have like few characteristics of the filters, like what is filter and how we can define a filter. So filter is a two-port network in electrical system that performs operation of passing the signal for a certain frequency band and rejecting other frequency band. So we have seen a filter as a two-port network. So in electrical systems, we have analyzed two-port networks in various forms. So a simplest two-port network is represented as a black box. So say this is our input port, this is our output port. So this is our black box. So in our electrical system, if we say this is a input port, so the signal could be a voltage or a current, and this is a ground signal. So signal line and the ground line for port 1. Similarly, we can have a current or a voltage as our driving point measuring quantities. So we have seen in our circuit analysis, if we want to define this black box in terms of these quantities, so we can define various transfer characteristics of this device, which is called transfer function. So it could be voltage at the output divided by the voltage at the input. Suppose if this is I and this is input, this is output. So transfer function is basically relating the input to the output. So suppose you have certain inputs, if you know the transfer function, then you can predict what would be the output. So just consider in terms of a filtering device, you know what's going to be the input, you want certain performance, like certain things to be, certain transfer function from this device. That means you are somehow rejecting something and you are accepting something through this black box. So this transfer function is really, really important, and it is defined in terms of the measuring quantities. Okay. So let's take an example for like simplicity. This is like a black box. So let's have a 2-port network, very simple 2-port network. So just take so this is a simple LC network. So this is L, this is C, and we want to measure or calculate or evaluate the transfer function for this network. So suppose we are working with the filters in frequency domain, so let's convert the whole problem into the frequency domain. So this impedance would be in frequency domains, we can relate with the quantity S. This is complex frequency, and this impedance we can say 1 over SC. If we apply the KVL, so we can see output voltage is equals to so it's really simple. This is the impedance, this impedance divided by the sum of all impedance. So the impedance, the reactive impedance by inductor is SL, and the reactive impedance by the C is this. So if we solve this equation, so we can find this can result in a transfer function like this. So we see the transfer function is a function of S, which is a complex frequency, and the quantities like the inductor value and capacitor value, and with some sort of functions associated. So if we know this from Laplace equation, S can be represented as sigma plus j omega. So we can replace this, and if we assume the system to be lossless, there is no losses, so this S could be replaced with j omega. If we replace this S with j omega, so we'll have a function which is in terms of this transfer function in terms of j omega, and we can take a magnitude of this to see how input is translated into the output. As this is a function of frequency, so by properly choosing the transfer function, you can somehow predict with a certain set of input frequencies what gonna be the output. So based on this theoretical background, we'll try to lay out what are the different kind of filters. So based on the transfer function that in the previous concept, we have predicted like there could be a multiple kind of filters. So let's see this multiple kind of filters with the kind of illustration, like how we can show those filters. So suppose this is a frequency scale in omega. So because we are like defined our transfer function in terms of omega, so let's talk about in omega domain. So this is, say, suppose a magnitude, and you have multiple omega 1, omega 2 and omega 3. So this consider this as your input, and here is your filter with transfer function something like this. So consider this as h of j omega mod, and this quantity as a 1, and consider this frequency as omega 2. So if this gonna be your set of input and this gonna be your transfer function of the filter, see, so this is our filter, this is our output, and this is our input. So we have defined earlier also the h of j omega could be v of j omega upon v of I j omega. So suppose this is our input, this is the transfer function. So in frequency domain, if we want to calculate the output, we need to multiply these two together. So if we multiply these two together, so what gonna be resultant spectrum? So the omega 1 could be multiplied with some sort of 1, so it remains unaffected, this frequency component. Omega 2 is on this edge, which is in magnitude slightly lower than the 1. So it gonna be reduced by some amount, say omega 2. And for the omega 3, which is quite far, and maybe suppose if we choose this as a location, so this component would be very, very low. So let's see, this is omega 3. So this set of input, here is our transfer function, and then this could be the output. So what we are doing here as a filter response, we are not affecting certain frequency component. There could be one limit where we can say this filter response is starting its stop band, and then suddenly we see like how transfer function is falling off in the stop band and how other frequency components get attenuated. So if we say, if we need to define this transfer function, so it passing all the lower frequencies, it's rejecting higher frequencies, so it's passing low frequencies. So this filter is known as low pass filter. So one of the type of filter is low pass filter. If we somehow change this transfer function a little bit, like that, and if we say this transfer function is somewhat like this, and this is our frequencies, and we define this as our omega 2 and this is omega 3 and here is omega 1. So if we multiply this input with this transfer function, what gonna be changed here? It's gonna be changed like this. We have strong attenuation at this frequency. However, there is one cutoff frequency and then this frequency component not gonna be suppressed. It's gonna be something like this. So what, like by changing the transfer function, the transfer function of the filter, if we have the same input, what filter job is doing here? It's rejecting lower frequencies and it's passing higher frequencies. So if it is passing higher frequencies, so this is called high pass filter. So what other combinations it could be? There are many combinations. It could be a band pass filter. So suppose we have a low pass filter, we have a high pass filter, and if the cutoff frequency for low pass filter, say suppose you have near to omega 3 or just define like it's omega 3 only for both the frequencies. And the cutoff frequency for the high pass filter is omega 2. So if these two filters can be simultaneously like made within a same transfer function, so it could result in a band pass characteristic. The resultant characteristic would be something like this. So this is a kind of band pass filter. In frequency domain, if we multiply two transfer functions, a low pass transfer function and high pass transfer function, then we can have something like band pass filter characteristic. And with the band pass filter, what it gonna change here in the output, it would be like it will have certain attenuation at this cutoff frequency. The middle cutoff frequency gonna be transmitted, and this is the cutoff frequency for the low pass filter. So this is band pass response. If any signal is in this region, so it would be greatly attenuated. So there could be one more combination of this, which is called band stop filter. So imagine with the help of low pass and high pass, how we can make a band reject filter. So just we need to flip these frequencies. So low pass filter gonna be like this, and then high pass filter gonna be like this. So we can have a band stop filter as well. So these transfer function basically define the output response with the kind of certain input frequencies, and this is how whole filter performance and their characterization is being carried out in literature. So low pass filter, high pass filter, so based on the nature of their transfer function. So we have taken a very simple transfer function with one R and capacitance. So we have derived the transfer function for this network, and we have obtained the transfer in terms of omega. And if we assume like 1 over RC as one of, because R and C are the values that we're gonna choose if we define as a constant, say omega C. So this whole term, if we take a magnitude, it will result in this sort of transfer function. So we need to observe this transfer function very carefully. So this transfer function, say I'm writing over here again, h of j omega magnitude, which is equals to 1 over 1 plus omega over omega c whole square. It should be square root, I guess. So if we observe this, say suppose for omega is equals to 0, so low frequency. So if we solve this, h of j omega for omega to 0, this gonna be 1. this is going to be 0, so this is 0, everything is 1, and then 1 divided by 1 is 1. Now, if we assume omega equals to omega c, so if we solve this, so h of j omega equals to omega c, so this is going to be 1 square root 1 plus 1 omega c divided by omega c square. So this is going to be 1 by 1 plus 1, which is equals to 1 divided by root 2. Okay, so in terms of c, when we are like at omega c, this omega c is related with the values of r and c, and the transfer function is slightly lower than 1. So we can say this kind of combination is giving us a low pass response. So for lower frequencies, the transfer function magnitude is 1, and then if we go little higher at say omega equals to omega c, so its value is getting lower with 1. So this is one of the type of transfer functions. So there could be multiple combinations of L and C, R. So at micro frequency, usually we don't use R. So L and C, so various L and C combinations can result in various transfer functions, and the magnitude of those transfer functions can be plotted to see the nature of the transfer function. So this is the example of low pass filter, and we can see in this course consecutively there are various transfer functions that can result in various other kind of transfer functions. So the other combinations, something like high pass filter, so they could result in high pass filter. So there are various other combinations. If we say choose the position of these components like different topologies, we can also result in a high pass filter.